afternoon, everyone. Okay, so welcome to another edition of this meeting. And last week, those of us who joined, we did a lot of OLS and some ideas behind the intuition behind all the regressions that we run and various extensions and all that data sets, how we compute them and everything. But in reality, we don't do everything with our hand. Like, for example, last week we were solving for beta naught and beta one. The data set was very small, so we were able to at least calculate certain things. But imagine we have a large data set. Can we do everything by hand? Obviously, we cannot do that. So we have to resort to some heuristics or some shortcuts that will help us to actually compute these betas and alphas if we want. And one of the ways that we can do so and do so easily is the use of STATA, or some people will say STATA. It's STATA. And this is the software that we are going to leverage today and maybe probably in the future to really dive deep into the application of the methods that we learn in this course. Okay, so to start, the first thing, obviously, you need to have STATA on your laptop or computer that you are using. And if you don't have, I would advise that maybe you can get one. And if you can open it and we practice along, that would be very, very helpful. But if you can't, you can just watch. It's going to be like easy to follow and everything. So I hope by the end, you can do it on your own. Okay. So let's move to our STATA. Okay. I hope everybody can see my screen. Oh, let me share again.
Yes, we can see your screen.
Oh, sure. I'm coming. So having the same challenge again. Okay, so this is the interface of like STATA. When you open it, you will see certain things like this. We see some rules and everything. In the first time going to be like a little bit complicated for some of us. Yeah, I know. But we are going to go through one by one. And hopefully by the end, everything will be super, super easy. I hope so. Okay, so let's start. Okay. Can you see this bar here? Like, can all of us see it?
Yeah, I'm sure they should be able to see it. Yeah, everything is they can see
Okay,
everything.
okay,
Yes, yes. All the
okay.
toolbars are visible. Yeah.
Oh, sure. Um, these two bars, okay. First of all, let's tackle them one by one, or some important ones that we are going to use often. So the first one, which is data editor edit. Okay, so suppose we are going to work with data, obviously. So later we're going to run regressions, but I want you to give a general knowledge about the data, the environment, so that when I'm doing something, it doesn't get complicated to some of us. I'm not going to dive deep into it because you can learn on your own as you are applying different tools and skills. You learn certain things along the way. So don't be scared that you have to do everything. No, you will learn as you go. So I'm going to give some introduction, then we get into regressions and learn some hypothesis testing and all that. And hopefully everything makes sense. Then call it a day. Okay. So when you load your data and you want to view it and maybe edit it or clean it, as we call it, we usually use data editor or to bracket edit. This will allow you to view your data and edit it. And we have data editor browse. And the difference between these two is for the data editor edit, you can actually edit. your data set. But for the browse, you can only what view it. You can only view it. You cannot edit it. So let's say you have imported some data into it, then you want to view it, how the data looks and everything. You click on data editor or browse. You don't have to even click it. Later you see you just have to type it and everything will come. And we have the variables manager. This is very important because that's where you can maybe augment your variables, change the names, everything. But again, there are shortcuts. Like you don't have to go through everything, like the toolbars and the tools and all the icons there. Okay. Another thing, you come back to here later, which is the do file. So we'll come back here later. Here we have the command pane or the command, whatever the command pane. That's what I usually call it. And this is where you usually see your commands, all the commands that you run in Stata. You see them there. And when they are in red, it means they didn't run, right? So when you see red, don't panic. Like when you see some red, and that means your command didn't go through. You need to check it out again. But don't be panicking because it happens a lot. You just have to see it and address the issue. Okay. And we have the variables pane. That's what I also call it here. That's where you see all the variables. If you import a data or you bring in a data set, you see all the variables, the names, the labels. The labels refer to the description of the variables in that data set. And we also have the properties of the variables. And here, you can actually change the name of the variables. You can change the labels, everything. And why do we need label? Okay, label is very important because let's say you go for a data from maybe a secondary data. That means the data you didn't really collect. That you don't even know the data, right? You don't know how like what this stands for because sometimes the variables, they use shortcuts to name the variables, as you will see later. So you need the label to actually describe the data that you are dealing with. And we have this large area here. This large area represents like the source window. And this will give you or will show you where your results, like how your results appear, or this where your results will appear actually. When you run your regression, when you do everything, your results will not appear only if maybe you are graphing your data, then for that another window will come, then you will see how your graphs look. But usually you will see your results here. And we have the command pane or the command window, whatever. Here, that's where you type your commands, and when you type them, then you run them, you see them here. If it runs, it runs. If it doesn't, it doesn't. Right. And one thing I would say as a caveat, like this is not going to, this data is a machine, like garbage in, garbage out. So when you do wrong thing, don't expect data to correct it for you. Like you need to reason with what you are doing, everything that you are doing, you need to think about it, whether it's right or wrong. Right. So whatever you do, it will bring it out for you. If it's garbage, it's garbage. If it's rubbish, if it's rubbish. If it's good, then it's good. Right. Okay. So now we know how we are around Stata. So let's move on to one of the most important things about Stata. So let's say you do your analysis, you deal with data, you crash everything, then the following day you want to run it again and see how do you do it? Do you start everything all over again? The answer is no. We have like a script or some place that you can write all the commands that you wrote. Then later you can save it. Then later you come back to it. Then you run everything again. And that script is called the do file. And this is the do file. We call it do file, do and file. It's very popular. I know those who have used Stata before have heard about it. And it's very important, especially in academia, to when you are submitting a paper to a journal, or they will demand your do file or whatever software that you are using. They will demand that you bring the actual process you follow to analyze your data. because they need to be able to replicate your results. You can't just say that I got this result. They have to do it and see whether you did the right thing with the data set that you are working with. So the do file is very, very important. So usually we work with the do file, so that everything will come back here. We usually work with the do file so that later when you need it, when you need everything, you can just come back to your do file and then continue or do some augmentations. Okay, so that's most of the things that we need. Now we have a general idea about data and everything. So we are working with data. So let's bring in some data sets. There are a lot, I don't know. There are various ways of getting data sets. One is your own data. Yeah, you can bring in your own data, like in Excel form. And other ways is STATA for your analysis, for just learning. STATA has inbuilt data set that you can use. And we are going to use some of them today. And hopefully I can import my own data set, though we are not going to run the regression because that kind of data is not suited for OLS. Okay, so let's start with the data sets in STATA so that you see how everything goes. So the first thing, you go to your file. There are shortcuts of doing that, but to make everything simple, go to your file and go to example data sets, right? You can click here and click here. Let's do this first. You can see various data sets, auto2, there are various data sets that you can use to practice, right? So let's pick the first one, use. Okay, so now you see when we run the first command, you can see it here, which is sysuse auto data. This simply means that we are using systems data, and that data is called what? Auto, and it appears here. Okay, so you've seen some changes here too. The variables pane, right? We have the variable name and the label, variable name, label, variable name, label. So for rep 78, if we hadn't written something about it using the label, you wouldn't have seen or known what that variable represents actually. So the repair records 1978. So now you get an idea about the variable that you are dealing with. So the label is very, very important in addition to the variable name. And as you can see, all the variables are in small letters. And it's good to name your variables small letters if you are actually inputting your data. Best to do it that way because in Stata, everything is case sensitive. If you type with capital letters, you can't also type small letters and expect to get the same thing. So to make everything simple, you use small letters so that you move fast. Okay, so now we've loaded our data. How do you know? You see the variables here. So we need to view them. We have two ways of viewing. We have what? A browse, which is you are just viewing it. You are not going to make any edits. And the next one is edit, data editor edit. That means you are going to edit your data actually. So let's just browse it. We can just click on it, but we can do ER, then browse. Okay. So this is our data sets. Can go through. This is the price goes down, and this is what the PD stands for what? Mileage. And repairs in record in 1978, everything goes on and on and on up to this point. So we have domestic and we have foreign. So whenever you bring data in Stata, the first thing, check your data, see if everything is right. Don't just go straight forward. Check your data. Are there missing values anywhere? What happened to that missing value? What can you do about it? Are you going to leave it? For example, I think I saw some missing values here, like this. We have some missing values there. Why that missing value? What's going to happen to your analysis if you have missing value and everything? Are you going to like extrapolate or do anything with it? These are the kind of questions that you need to answer yourself. So this is actually very difficult when you have a large data set and you really want to do something with it. Sometimes very difficult and the data is messy. This data is very, very clean, as you can see. But when you go for data from maybe some institutions, sometimes it's very, very horrible to really work with that kind of data. You don't know what the variables you even represent. They didn't label it, they didn't do anything. So you have to go back and forth with the institute and really, it's a lot sometimes, you know. So I hope the journey is at least fair to you and sometimes very nice to us a little bit. Okay, so this variable, which is called foreign, is in two folds, like domestic and foreign. So it's more or less like a dummy variable. Remember last week we did dummy variable regression, and hopefully we are going to do some with this variable. Okay, so you can see red here, you can see black here, you can see blue. What does like they mean? Like what do they mean is different? And why is some in red, why is some in black, why is some in blue? The red simply means that they are strings like words. String. Like string. String means letters, words. And the blacks are numerical values and the domestic is like categorical value or call it sometimes they call it label. Okay, so when you see the string, it's very difficult to do some computations with strings. Like they are not numeric. So when you are working with them, sometimes you need to do something with them before you can work with them. But in our case, we are doing pure quantitative. So sometimes it's very difficult unless we are using machine learning to do some. Hello? Okay, so unless maybe you are using machine learning to do some maybe classifications or whatever. But for now, we are going to restrict our attention to domestic, to numerical values and some categorical values. Right, so we've checked our data. We have imported it. We have our question. So we want to, this is the price of a car. Actually, the data is about cars and mileage on them, weight and everything. So we want to find what determines the price of cars, right? So last week we started with simple linear regression, which is we have a dependent variable and an independent variable. Then we have our betas. And our goal was to what? Estimate the betas very, very well. Why very, very well? Because usually we use samples. We cannot get data for the whole population. So we use some sample. And because of that, we want the sample to be very, very representative of the population so that the values that we get actually represent the population, or else we are getting garbage results, right? Okay, so how do we estimate our betas? We talked about it last week. But before that, let's form some questions that we can use. I know this is very wrong, but let's form some questions that we can answer because we need to have your question before we can actually look for your data set, right? So we have our price here and we have make or model. We have this, we have that a lot. So let's first regress price on make or model. They didn't really describe the make or model here, what the make or model really represents. So sometimes very difficult. Okay, so let's do the mileage. Mileage, I think mileage is a little bit better. Let's regress this on MPG. Okay, the make is cannot work with them. So let's do the mileage. How do we do it? The first thing is data. When you are doing any computation or anything, you start with your command, then you bring your variables, comma, then you specify options. That's the generic specifications of data commands. You bring your command that you want to invoke, then your variables that you want to apply that command to. Then if you want to specify additional options, then you bring your comma, then you specify that option. I know it may be complicated for now, but as we are learning, everything will become very, very simple. We'll pick everything along the road. So to run your simple linear regression, and our data is cross-section, right? Cross-section. So we can apply our OLS. And whenever you open your Stata is assuming that you are going to use cross-sectional data. Whenever you're going to use um, panel data or time series data, you need to specify that the data that you are going to use is what is time series or panel data. Then you have to write something before you run your regressions, like ST set and TS set. They are all there. But because you are dealing with crosses now, you don't have to specify anything before that. So everything starts with the data, the kind of data that you are working. Otherwise, your results will be garbage. Okay, so let's run our regression. So you bring your command first. What command are we running? We are doing what? Regression. Okay, so reg, that's the short form for it. Then you bring your dependent variable first. Your dependent variable first. Okay. If you bring your independent variable first, Stata will do the same, as if that independent variable is a dependent variable. I said garbage in, garbage out. Okay. So what's our dependent variable? The price. You want to find the effect of mileage, like on price. And you start with your dependent variable, then followed by what? Your independent variable or variables. So this time we are dealing with what? Simple linear regression. So we have a single dependent variable and an additional independent variable. So we bring our data, which is MPG. You can type everything if you want, but it's very, very easier because it's less likely that you are going to make a mistake when you pick everything from here. You just click and everything. But when you are typing, you could make some mistake, especially when the data set is very, very messy. So after everything, you just click on enter. As I said, you can specify certain things along. In the future, maybe you add robots to it, but for now, we haven't learned a lot. So let's pause everything here and let's run this regression. Okay. So as I said, output is what? Here. This is the output. I know it's a lot, but will be the normal became. So let's demystify everything. Okay, so as you can see, the price is here. Always you see your independent variable here. And your what dependent, you see your dependent variable here and your independent variable here. And that's CONS represents the constant, which is what the beta note that we did last week, the beta note. The value for that is this. And the value for the slope coefficient is negative 238.8943. So we can rewrite everything as price is equal to 11,253.06 minus 2.38.8943 what miles per mileage. This mileage, not miles per anything, mileage. So that will be our regression, our regression that we fit. So after fitting your regression, that means getting the value. Mind you, OLS did what we did last week. It took everything, subtracted everything little by little, and got this value. It's not like anything like black box. The same thing that we did last week. That's what the Stata did for us. So the same process. Okay. So after everything, we should what? Interpret. How should we interpret? Pick them one by one. Last week, we said the constant, which is this CONS, the short form for constant, which is this, represents the value of the average value of what? The dependent variable, which is price, given that the independent variable, which is what? Mileage, is equal to 0. So this means that when when there is no mileage on the car, that means EMP, right? Car EMP. Yeah. And the price of the car is what? 11,200. The average price of the car is 11,253.06. The car is new, like manufactured, newly manufactured. Average price is what? 11,253.06. I think it makes sense. Then the mileage, like how does mileage affect the price? Which is what? Negative. Why negative? It makes sense because the more you like the car is like being used, the lesser the price because you're trying to condemn like something like that. Yeah. So the newer the thing, the higher the price. The older the thing, the lower the price. So that's why there's a negative relationship between mileage and price. The relationship was positive. That wouldn't make sense. So I think this is a really, really good estimate. Let's post this a really, really good estimate. Okay, so how should we interpret it? Last week we said this represents how much price would change if mileage increases by a unit. I don't know the units that they measured the mileage in, so I'm going to assume just a unit. So if mileage increases by one, I don't know say, if it's kilometers or whatever, if mileage increases by 1 unit, then the price of the car will decrease by 238 will decrease. Don't say it will decrease by negative 238. Doesn't make sense. Decrease is represented by what? The negative. So if it were to be positive, it would have what? Increased. That's because mileage actually decreases the price of a car. If mileage increases by 1 unit, then the price of that car will fall by what? 238.8943. I don't know whether it's in dollars or in whatever the currency denomination. All right. Any questions so far? Any question? 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 I think someone was talking.
Someone is talking.
Hello?
Maybe the person can unmute so that we can hear him. Yeah.
Or just a H?
Yeah, Gabriel, you can continue. I
Okay.
don't think we have.
Okay. Okay, so let me continue. Okay, so last week, this is kind of where we ended. We were able to estimate and we talked about confounding variables and the rest. So if last week you weren't around, you can just go back and just watch, and after that, this will be uploaded. Then you come back and watch. Everything makes sense. Okay, so let's go on and like review our results. Now we can see this, which is called standard error. Standard This represents the standard deviation of an estimator. You know, the betas, they are all estimators. Why are they estimators? Because we kind of have a population like value, and we are trying to what, estimate that population value. Because if we could get the whole population, we could have gotten the real value, but we got a sample. So the betas are actually estimating something, which is the population parameter, right? And because one thing, let me be a little bit like, wayward a little bit. The sample size that we draw every time, remember, we are dealing with sample size every time because we cannot get the whole population. We are not using the census or something else. It means that the value that you are getting is not actually the true. We cannot know, and we cannot know whether we have the true one or, but on average, you want to get closer to the true thing. And the sample size is random. Every time you can get a different sample. So for example, let's say you are collecting data on students like consumption on campus in K University. Then you start on Monday. Then you collect your sample, like 100 students. Then you estimate the average of that consumption. Then the following day, you get a different value for that. Then it means that the sample is what random, like it changes over time. So you are going to get different estimates. So because the sample size or the sample is rather random, then the estimate is also a random variable, right? And because of that, we will get a distribution of that random variable. Every random variable has a distribution, whether a normal distribution or like chi-square distribution and everything. And they will vary. Like we have the mean, we know the standard deviation, then standard deviation measure the deviation away from the mean. they will vary. So this standard error, what I'm saying is that this standard error measures the variation in that estimate that we are getting. The lesser the variation, the better. The lesser the variation, the better. So the lesser the standard error, the better our estimate, because the standard deviation, as we know from high school and everything, measures the deviation from the mean. But we want to get closer to the mean. So if the deviation is quite small, it means we are closer to the mean, right? So if the standard error is also small, we are closer to the mean of that estimate, which is the population mean that we are talking about, the population. If you remember OLS from, I think, third year, we said that like OLS is blue, unbiased. It means that on average, it approaches its population parameter. I hope we talk about that later. But if you didn't hear anything, know that if the standard error is small, it's better. Okay, so why do we care about the standard error? This standard error is very important because let's say you are going to a pool, then we tell you the pool, I don't know the feet actually. Let's say the average is maybe 10 feet. Then they say it's the standard deviation is 1. That means like it doesn't vary. The deepness doesn't vary. But we tell you that the standard deviation is 7. Then one of them you can get 17, you can die, right? So you need to know the variation is very, very important. The closer the thing is to the mean, the better. And we use the standard error for hypothesis testing. For example, when you are calculating your t statistic, you do it like beta naught minus that over the standard error of that, right? Okay. So to move on, this is the standard error of the estimate that we got. Rather huge. If you can get something to compare, it's rather huge. And this too is the standard error of it. And this is the t-value that I calculated for it, that we can use for hypothesis testing. But we are not going to resort to the t here. We are going to resort to the p-value. If you haven't heard of it, I'm going to explain. What does the p-value does? Which is this p-value? Why do we need a p-value? Why do we do hypothesis testing? We have estimated our coefficient. We got -2, blah, 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 and this. Why do we even need this here? Remember that we are using samples, right? And the sample can vary. So we want to tell whether the estimate that we actually got, is that really different from 0? Because we are doing a sample, we are not doing the whole population. But we want to know if that. Hello?
Continue.
We want
I
to.
muted it. I think it was a mistake. Yeah.
Oh, okay. So we actually want to know if it's not different from 0. Like if it's 0, then that has no effect on it. So we need to test that hypothesis that it actually this coefficient is not equal to 0 or equal to 0. So usually you form your null hypothesis before your alternative hypothesis. Then we calculate our p-value. Then we compare it to 0.05. And if the p-value is less than 0.05, then we reject the null hypothesis, which says that the estimate that we got is 0. It's actually equal to 0. I know some of you may be like, but this is not equal to 0, so obviously it's not equal to 0. Remember, we are dealing with samples, so if you have a different sample, it may not be different from 0, right? But so we want to actually test statistically if that estimate that we got can be 0 in some sense. But this is a sample, so it may be some like extreme case. So the p-value will tell us whether our the null hypothesis is rather strong or not strong. So the p-value measure the probability that okay, I don't want to give the estimate. Let's pause here, otherwise it will make people confused. Let's pause here. So the p-value, your p-value is less than 0.05. Then you reject the null. Then you conclude that actually this value that we got, -238.8943, is rather not equal to 0. So it's significant. That's why we say that value is significant. It actually has an effect on price. So when we are determining the price of a car, we actually envision that, okay, what's the mileage of the car? Because mileage actually has a significant effect on what the price of the car. So now let's check the p-value of it. We said if the p-value is less than 0.05, which is 5%, in social sciences, we often resort to what 5%. You can also actually go beyond that and say what 1%, then 0.01%. In the medical sciences, they do that. And in some political science, they use what 10%, which is what 0.1. Okay. So our p-value is 0. What does it mean? It means that this value is very, very significant. Mind you, I said if the p-value is less than 0.05, you reject the null hypothesis. The null hypothesis is what? That is equal to 0 statistically. But if the null hypothesis, this is less than 0.05, you reject that null hypothesis and then accept alternative. The null was that it's equal to 0. So the alternative will be what? It's not equal to 0. So if you reject that, what alternative equal the null hypothesis, then we go with what the alternative, which is what the other estimate is not equal to 0. So when you check your p-value, compare that to the 0.05 in economics, that's the norm. Then you see, yes, this is less than 0.05. So we conclude that the mileage of the car has a significant effect on the price. The other one is the constant. Sometimes we are not really interested in the constant, but in this case, we are interested in the constant because it tells us the average price of a new car as we interpreted. So for this two, very significant because it's less than 0.05. So we conclude that this is significant. What if it was larger than 0.05? Then you can see that the mileage of the car actually doesn't determine the price of the car. So that's the conclusion. Right. Any questions so far? No. Okay, so let's move on. What about this? It's a confidence interval. What's a confidence interval? Confidence interval is more or less like a set. To be more rigorous, it's like a set. That, on average, like 95% confidence that it actually contains the true value. What does that mean? When you are doing your analysis, you are dealing with sample size. You are not dealing with the population. So you cannot really know the correct value. So you want to actually form some set here. We can say that, okay, the population value actually ranges from, can be like negative 344 point something. Between that range, we can actually say that, right? That's one of way of like do your analysis. Because if you are able to at least say that the value is between this, you can actually make some analysis with it. In this case, it's negative, like the whole thing is what? Negative. So you can say that, okay, then population value can be what? Negative. So we can actually advise that, okay, when you drive car more, then the price, when you are reselling it, the price will go down because the value, the confidence interval like is negative. Or we are expecting it to be negative because the confidence interval that we constructed is actually ranging from a negative value to a negative value. Here too, the same thing, they are all hot positive. So we have an idea. So confidence interval, like we are constructing an interval that on 95% confidence that the value, the population value is within that confidence interval, the interval that we are constructing. In a way, some people like confidence interval than this like this point estimation and this confidence estimation. This point, like we are in a specific value because some people love confidence interval as opposed to the point estimate because confidence interval like at least make some room for some error. Now I'm moving into statistics in more detail a little bit, but to get the intuition, some people really like the confidence interval because it really gives some room for error. Because we are using sample, we are not using the whole population. So let's say you want to know the average age of all youth in Ghana, then you go to only Care University, then you average, like you find the average age of them. Actually, there will be some error because if you could have gotten the whole population, the youth, then you average everybody's age. then you could have gotten the real value. But obviously, taking your sample size from Oniki University, there will be some error in there. So you can form some confidence interval like, okay, the average is between this and this. So you'll be confident that, okay, the value is between this and this, as opposed to getting a specific value, which can be wrong in a certain way. I think it's fair enough, right? And the last thing that we are going to discuss, then we move on to another example, then we interpret, you go through again so that the other time you can do some practice more. Which is you can see something called R squared. R squared tells us like how best our model that we formed, which is price as a function of the constant and fits the data that we have. How does it really best fit the data that we have? And it ranges from 0 to 1 or 0 to 100%. And the closer the R squared is closer to 1, the better our model, which is this, fits the data well. Don't forget that we are fitting a line between in the data set, right? So if the line doesn't really fit well, we are going to get poor like prediction if you are making prediction with it. So let's check. R squared is like 0.219. In fact, it's not really good. R squared is very, very small. Usually you can get 0.99 something, which is very good, which really fits the data, because when you get that, it means that your model actually like tells us everything that's happening in the data set, right? So this means that we need to add some variables in our regression so that we can make use of the full information in the data set, right? And we have adjusted R squared, which is closer to R squared. Anyway, adjusted R squared is always smaller than R squared. I don't want to go into details about adjusted R squared, but notice that they all measure how well our model fits the data that we are using. Is it fitting it well? This will tell us. We have another ways of doing that, but for now, for introduction, whenever you do your interpretation, you have to also check the R squared and see whether it's really high or low, and maybe if you can do something about it. But usually don't believe, like, bore into it, like my R squared is very low and all that. Okay, so let's do another regression. The same thing, same price. I prefer doing this. And price, then mileage again. And also, let's let's do the weight of the car and see whether the weight actually affects the price of the car. And let's run this. Always bring your dependent variable first. And you go try this model this regression that we run. Reverse everything and bring the mileage first, and you get a different result. Even if you get a simple result, the interpretation will be different. A similar result, the interpretation will be different because the dependent variable and the independent variable has shifted, right? Okay, so let's run this, and we have a different one. So now we have our constant here, our coefficient for weight, and our mileage value has well changed when we accounted for weight, right? When we accounted for the weight, the value has all changed. When you controlled for it, we call it control for it, the value has changed. It means that there was some. Remember, I think last week I said it. The variables that we didn't include when we were running this regression are all in some variable called, sometimes we don't use a variable. We call it the error term. So the weight was also in the error term. So when we accounted for it, you can see that the value, like the effect of mileage on the price has actually reduced, right? So it means that you need to have to actually think about it and include the necessary like variables in the regression. Suppose that you went to a like a CEO and CEO of a car maker, then you told him this. Later, someone comes in, then after controlling for you, you realize that the value has actually got come down. You see the dynamics. We could also add another variable then. So always think about it and include the necessary values or the variables in the regression. Otherwise, you get some way. misleading results and everything. So now let's check the p-values. You can see that now this is actually larger than 0.05. So what does it mean? It was significant here. Here, it's not significant. It means there may be something wrong, right? But this still everything, in fact, 0.05. Okay, so this actually is still significant. The weight is significant because it's less than what 0.05. This is 0.008. So actually in this model, our weight, the weight variable actually has a significant effect on the price. But the mileage actually that doesn't determine the price, right? So people don't care about the price, the mileage of the car if they are checking the price, which doesn't make sense. People usually do. So we have to really do certain things. So I think by now we are getting some overview of it. So now let's check the R squared again. Now the R squared has increased. Usually, previously it was 0.2196. Now it is what 0.294. So some people can say that, okay, then let's add more variables to increase our R squared. Mind if you also include like unnecessary variable, there may be some consequences. Later, you will learn all these things. So when you include all the right variables, you get the right results for yourself. Okay, so let's do more regressions and hopefully. Initially, I wanted to call someone so that the person can do the interpretations for me. So I don't know whether that would be better for us or time allow us, or can someone do it for us if there are any interpretations that I want someone to do for us?
The time is not doing very well with us right now, but then I think you can call someone if you want someone to do the interpretation because this is a new regression. So maybe
Oh,
we
okay.
can do that one, then maybe you can wrap up. I think we are almost hitting an hour. Yeah.
Yeah, okay.
Yes.
I want
So
to,
please feel free to call someone, please.
okay. In fact, I want to do our last regression, then we are done for the day
Okay.
then.
Okay, sure.
Okay.
Okay.
So last week we did some dummy variable regression. Like when you have a variable that is categorical, it can be 0 or 1. It can be, for example, male, female, like foreigner, like immigrants and citizen, those types. So from our data set that we browsed earlier, let's do it again first. We see that foreign, this variable is what is categorical. It can be what domestic and it can be what foreign. So we want to find out, does the origin of the car affect the price of the car, right? So we can regress price on what foreign variable and see if we are limiting ourselves to a simple linear regression. So let's do it and see. Okay, so we have REJ. Then the first is what? Dependent variable, which is the price. Then the next one is what? Your independent variable. In this case, you want to find the effect of what? The origin of the car, which is what car origin on the price. You want to see whether domestic cars are more expensive than foreign cars or vice versa. So we have our regression. This as simple as it can be. So, okay, so we have our results. The result says from last week, this will be the value for the zero category. So in our case, what is the zero category? Let's browse and see. The zero category is what? Domestic. How can we see that? We can see the zero from here, right? So constant represents the value, the price of average price of domestic cars. So the average price of domestic cars is called is $6,072 or Ghana cedis. And this here represents the difference between foreign cars and domestic cars. So it's positive. So foreign cars will be what? 6,072 plus this 3,000. So this is the difference between domestic and foreign. So foreign cars are more expensive than our domestic cars from this estimate. Now let's check whether the values are significant. This means this constant has a p-value of 0. So it means that it's very, very significant. The difference doesn't have any significance here, as we can see. So what can we say? We can see that we don't reject the null hypothesis. We fail to reject it that there's no difference between foreign cars and domestic cars with respect to what prices. So in conclusion, we can say that foreign cars and domestic cars are cost the same. They cost the same. And the R squared is again very, very small. So we need to include some variables. So I think we have done enough for this introduction. And hopefully when you go home, you can browse more data set and play with them and do your interpretations and all that. I hope in the future we move on to this or all of these things differently with different speakers. So any question?
Yeah, hello guys. Please, if you have a question, you can let us know so that Gabriel can answer you.
Hello.
Okay. Yeah, Gabriel, I think we don't have any question.
Hello, hello.
Okay, someone is Daniel. You have a question? Okay, please go
Yes,
on.
please. Uh, I, I wanted to have a clear explanation of why the mileage is insignificant in the second regression.
Why the mileage is significant, is not significant.
Yeah,
Oh, uh, for that, I would say the answer depends on the kind of data that you are working and the controls that you included in. We cannot be sure. Maybe let's say we add another variable, the relevant variable. It could be what significant. This is a statistical question that you're asking me. In fact, I cannot answer that. That why is it not significant? Maybe it actually is not significant. So we can say that because we didn't control for weight initially, but when you did, it's not significant no more. But it could be that if we added another variable, it could have turned significant again. So it depends on the data that you are working, the quality of the data and everything that you are working. So this is a really, really difficult question. I can't give a definite answer to that, why it's not significant. Because from our knowledge, it should be significant, right? So you need to check your diagnostics and everything to see if everything is going well and what is affecting everything. So this is just an introduction, so we cannot go into every diagnostic and see where the issue is. So that's the answer that I can give, Daniel. So if I have answered your question, I know I didn't answer it, but I think
oh,
you have
thank
some
you.
about
Thank
it.
you very much.
Okay. I don't know if Team as we can also add certain things to it.
I mean, you said everything, and the most important thing you said is we can't consider all the things that made marriage, right,
Yeah.
insignificant because we have to look at whether, I mean, the identification strategy is correct and all these things that we can't look at here. But what you need to know is that the regression was run the right way, and there are a lot of assumptions that we've not yet actually broken them down. So, T. Gabriel cannot actually give you the entire picture, but I think the answer he gave you is the best answer that he can give you right now. Yes, thank you. Please, if you have any further question, Tia Gabriel is here. Please, you can uh, ask your question, please.
Hey, no,
Okay,
no
I
question.
think I think the time is up, so people have started
Yeah,
leaving. But guys, thank you
yeah,
so
okay.
much, and we hope, as we promised, we are gonna bring you more and more of this econometry series. So now we are going to break down the classical linear regression assumptions. We are going to go through them one by one, and so that we start expanding on our regression and explaining the reason why some of the variables are not significant, as Daniel asked. So thank you guys for joining, and hopefully you will hear from us and we'll bring you more exciting series going forward. Thank you so much. And thank you, Tia Gebra, for this wonderful presentation. A lot of people really enjoyed it. Like last week, I had contact from LinkedIn who were asking me whether they could get the presentation material and the video and others. So thank you so much for putting the work. And maybe we hope to see you soon, hopefully, in the intermediate or
Okay.
maybe the advanced econometrics. Thank you so
Okay,
much.
sure, sure,
Okay.
sure. Okay,
Yeah,
welcome.
have a good weekend. Thank you all, and
Okay,
we hope to see you guys soon. Bye.
okay, okay. Bye.
Thank you.